To check that risk-neutral probability is a probability measure, we must verify that risk-neutral probability of omega equals 1, and that risk-neutral probability is countably additive. We have by assumption risk-neutral probability of omega equals the integral over omega of z of omega with respect to actual probability of omega, which equals the expectation of z, which equals 1. For countable additivity, let A1, A2, and so on be a sequence of disjoint sets in F, and define Bn equal to the union from k equals 1 to n of ak, and B infinity equal to the union from k equals 1 to infinity of ak, because the indicator of B1 is less than or equal to the indicator of B2, which is less than or equal to the indicator of B3, and so on. And the limit as n approaches infinity of the indicator of Bn equals the indicator of B infinity. We may use the monotone convergence theorem to write risk-neutral probability of B infinity equals the integral over omega of the indicator of B infinity of omega times c of omega with respect to actual probability of omega. This equals the limit as n approaches infinity of the integral over omega of the indicator of Bn of omega times c of omega with respect to actual probability of omega. But the indicator of Bn of omega equals the sum from k equals 1 to n of the indicator of ak of omega, and so the integral over omega of the indicator of Bn of omega times c of omega with respect to actual probability of omega equals the sum from k equals 1 to n of the integral over omega of the indicator of ak of omega times c of omega with respect to actual probability of omega, which equals the sum from k equals 1 to n of the risk-neutral probability of ak. Putting these two equations together, we obtain the countable additivity property. Risk-neutral probability of the union from k equals 1 to infinity of ak equals the limit as n approaches infinity of the sum from k equals 1 to n of risk-neutral probability of ak, which equals the sum from k equals 1 to infinity of risk-neutral probability of ak. Now suppose x is a non-negative random variable. If x is an indicator function, x equals the indicator of a, then risk-neutral expectation of x equals risk-neutral probability of a, which equals the integral over omega of the indicator of a of omega times c of omega with respect to actual probability of omega, which equals the actual expectation of the indicator of a times c, which equals the actual expectation of xc, which is risk-neutral expectation of x equals actual expectation of xc. We finish the proof of the formula using the standard machine developed. When z is greater than 0, almost surely 1 over z is defined, and we may replace x in the formula by y over z to obtain actual expectation of y equals risk-neutral expectation of y over z.